Let's prove Cayley's theorem. So let G be some finite group of order n. And now let's say for some group element H in G, we define a map which we want to call phi H that maps G to G. And it does it as follows. It takes a group element G and maps it, well, of course, to phi H of G, and phi H of G is just left multiplication with H. So the dot here is the group operation, or I'll just omit it altogether. What does this phi H do? It just permutes the elements. So if we apply this phi H to all the group elements, it spits out all the group elements again, because that's one row in the group multiplication table. So it permutes the elements of G. It's a row of the multiplication of the group table. Now let's look at this map F, which maps G to phi sub G. So that's a map from the group to something I want to call G prime, some other group, which I define just as this set here. We collect all the phi sub G's with G's in the group. So these are the elements of our new group, and the group operation will be just composition of maps. What can we do with this? This F now is actually a homomorphism. So why is that? Let's look at, let's say, FA after FB applied to some group element G. So that's phi A of phi B of G, and that's just phi A of BG, and that's ABG, but that's the same as phi AB of G. That's true for all G. So actually we see here that phi A after phi B is the same as phi AB. So it's a homomorphism. And moreover, it's injective. Because we said that each of these phi's here, when we apply it to all the group elements, we just get one row of the group multiplication table. And there cannot be two identical maps here in this list of the different phi's, because otherwise we would get two identical rows in the group table, and that's not possible, because then we would have identical numbers in a column, which is forbidden. So it's it's injective, and of course it's also surjective, because by definition we just collected all these maps here, which means it's actually a bijection, this F here. So F is an isomorphism. So we can say that G is isomorphic to G prime. And G prime in turn, what's that? G prime contains all these phi's here. These phi's permute elements of G, n objects. So this G prime here, it's a subgroup of the group of permutations of n objects. So it's a subgroup of of Sn. So G prime is isomorphic to a subgroup of Sn. And that's exactly what we wanted to show.